So now we say, instead of using these cells, these n cells or n simplices, we can also use the characteristic maps of it. You should look back to characteristic maps of these cells which we defined before, and these maps which we write here are going to be similar but not exactly the same. So the characteristic map essentially acts on the n simplex and takes it to the x. It is nothing but a replacement of a disk. So we used to write dn here. Instead of dn we are writing delta n. So what does it mean? So take a 2 cell, that is a rectangle, and this rectangle, if you know the topology, you know rectangle is made up of disks, small 2-dimensional disks. Instead of disks you are using triangles. You see here, we're just going to break up the rectangle into small triangles. Similarly, a 3-dimensional space, we break it up into small tetrahedrons. So that is pretty much it. Please see page 103 on Hatcher to further know about these characteristic maps. Here we are just doing hand waving, and we are just saying that these characteristic maps, you should keep in mind the characteristic map for CW complexes and just replace that map with sigma alpha. So previously I wrote z alpha and e alpha n. I am replacing z alpha with n alpha so as to make notation consistent with Hatcher. Why I avoided writing n alpha before is because n has no relation to the superscript e alpha n. So again, this n alpha is an element of integers, just like in the case previously. So previously we had written z alpha e alpha n, now we are writing n alpha sigma alpha. So just let me write quickly that more on this is on page 103. Okay, so that is pretty much it. Now let us talk about the delta complex of such a thing. So we just wrote down the boundary map for complexes as such. What do we do with map sigma alpha? There is nothing much. We just so let us write down precisely. We go from delta n of x to delta n minus 1x, and this map is nothing. We just write down exactly what we had done before. So yeah, we write the summation sign, put I under it, sum over all I, then write minus 1 I. So instead of, we will again write the same n simplex and move the ith vertex, but right now we will write it as sigma alpha, which acts on this simplex. So sigma alpha is acting on this simplex. What it produces is not important. What is important is what it acts on. So yeah, to make it more precise, we write it like this. So this is the boundary map. So you see, we have done nothing. We have just defined a map sigma alpha acting on the face. The face is obtained from the original vertex by removing one vertex at a time. So this is the most important lemma. In fact, the lemma which lays the foundation of the subject. So the following composition map, you start with delta nx, then apply the boundary map, go to delta n minus 1, then again apply the boundary map and go to delta n minus 2. So this composition is 0. This is very important. This is actually the start of homological algebra. What happens here naturally? So we say the boundary of boundary is 0. So you first apply delta n, then delta n minus 1. Now the proof is really easy. So you first take j less than I. So first you remove vertex I, very easy, and then you remove j. So first when you apply delta n, you removed I, then you apply delta n minus 1 and you remove vertex j. Now notice there are j minus 1 indices before. So we have point 0, 1, 2, 3 all the way to j minus 1. So total of them are j positions. So 0 to j minus 1 are j positions. So second is j is greater than I. So these I have said 0 to j minus 1 are j positions, and that's why I have raised minus 1 to the power of j. So again now in the second part we write minus 1 to the power I and minus 1 raised to the power j minus 1. I need to explain why for the second index we are using j minus 1. The first index is clear. Obviously you first apply delta n and there is nothing there, so that is fine. So we first removed I. It's only in the second map you apply Vj hat. Now you see that the number of positions we are going to count. We start with index 0, 1, 2, 3 all the way to I minus 1. Then we skip I because I has been removed already, j is greater than I, and we go all the way to j minus 1. Now since I is removed, all these are nothing but j minus 1 positions. That is why minus 1 is raised to the power of j minus 1. Just put an arrow here so as to make it clear. So as you see, the first term is opposite sign to the second term, obviously because we have a extra minus 1 in the first term. So these two terms cancel out and what we get is a 0.